Yes, sure. I worked at the Max Planck Institute for Quantum Optics, and so we heard about this. We had talks about this, so I was well aware of this. Let me see. At this time, I was working on multiphoton excitations in atoms and multiphoton ionization, looking for distributions of photoelectrons. But in neighboring groups were closer to this field. But at that time, I did not see the immediate connection between the SNOM and the quantum optics world, partly because the SNOM in the early days had lots of losses. It was very inefficient, and this kills most of the quantum optics effects. So we were well aware of this, but I thought at that time it has just impact on resolution in microscopy, which at that time was not the immediate impact to quantum optics issues. So I think nano-optics is the challenging side of classical optics in the very small, describing the three-dimensional properties of space, where the spatio-temporal modes of light live. And quantum optics needs all this, and the only thing that is new in quantum optics is the excitation in the modes, how they are described, and correlation between modes. So basically, if you want to do optics at the advanced level, you need the combination of optics and quantum optics, or nano-optics and quantum optics. And I think as a challenging thing in the future, in this wider field of quantum technologies, where we will now have this flagship at the European level. So I think the challenge in this regime would be the quantum internet that people are talking about, where you need both aspects in their full power. You need to couple two-level systems, small atoms, whatever they are, small quantum dots, and and then you need to couple to them. You need to couple to them efficiently. That's very important for quantum technologies. So yes, I think you need both aspects in the maximum possible performance. So first of all, there was a gap because at some point I decided to leave academia and I went to Switzerland to a company, and after 5 years I had the offer to come here to Erlangen. That was in '94. And so then with my first co-worker, we were looking at possible things that we could do. And he dug out a paper on sonoluminescence, which was a hot topic at the time, and people had not understood. So sonoluminescence, if you remember, is sending in a spherical acoustic wave to a focus in water. And in the very center, there's a small bubble, and inside the bubble there was some blue light. And people were wondering how to explain this. And then I noticed that this bubble is much, much smaller than the wavelengths. And then I was thinking, how can this be? And so my coworker thought maybe we can go into this field and help discover what sonoluminescence is about. But my heart was more on the side of optics and light, and I was thinking, how is this in optics? And I mean, in optics we have the resolution limit given by the wavelengths, and so how does this compare? And then we were thinking of what nature gives us, and we were thinking about the emission and absorption of an atom. And if you look at spontaneous emission, then initially the atom is in the excited state, eventually it's in the ground state, and the photon is far away. And thinking of the word spontaneous emission, many people would have thought that maybe you cannot reverse this because spontaneous emission has this stochastic connotation, and stochastic statistical events you cannot reverse. But when we thought about it, it became clear that this is just quantum mechanical unitary evolution, and that it should be possible to go backwards. And of course, if you go backwards, all the light energy of a single photon goes into the atom, and eventually it comes to a point or to a volume much closer than the much smaller than the wavelengths cubed. And we were thinking, oh my God, okay, here's a possibility to concentrate much light much smaller on a volume much smaller than a wavelength cubed. And so then we were thinking of what kinds of experiments we could do. And then in the early days we were thinking, this will be difficult. But then we found that even if you don't have an atom, but you take guidance from this reversed spontaneous emission, that tells you that you should send in a dipole wave with the proper vectorial properties of light. And then we did the calculation. We discovered that focusing a dipole wave gives a focus which is as small as you can get. And this you can never achieve even if you focus in only. So ideally you have to come from the full solid angle, but even if you come from 1/2 space with a lens, linear polarization wouldn't do this job. You have to have a different polarization. So this is how we got into this. And apparently we were the first people to think in this direction. And then we also showed this experiment. So that was basically a spin-off from this initial thought, how about reversing spontaneous emission? And only when we had this first funding from Max Planck, when our institute was a 10-year track, then I decided to take the challenge and start the real project. Let me see. So I think, the names Nano and Optics separately I've probably heard a long time ago, but in connection I probably heard this when I came back from industry. So this would be the early 90s or mid-90s, early 90s. So if you say that nano-optics is everything in optics which happens on a scale smaller than a wavelength, one might think on such a small scale things are more or less homogeneous and not much is happening. But that is not true. So when you have interaction with atoms, small plasmonic particles, you have all this interaction, all the near field aspects. You can have zeros of the field which are surrounded by vortices, and these are structures which can be much smaller than the wavelengths and can be highly complex and interesting and have interesting consequences. And the interesting thing I find is that in this old field of optics, one discovers new things again and again. So if I think about my own research, so we discovered this focusing is possible in a different, better way. And we did this we started to think about this in the 90s, more than 100 years after Ernst Abbe. So many people having thought about light and focusing and vector properties. Whole books have been written on this, but this was not there. And then another thing that happened more recently is that an old optics topic is total internal reflection. And for a long time I thought I know everything about it. And then it was between the group of Anatoly Zayats and Arne Rauschenbeutel and my group that we understood in different contexts and in quite different experiments. We understood that the polarization has a very special property near the interface under the condition of total internal reflection. And you can have these spinning fields that we call transverse angular momentum. in the evanescent wave in total internal reflection, which is was a strong correlation between the sense of the spinning and the emission direction, which these groups that I mentioned have now shown that you can make use of this. So this, I think, is really nice that sometimes, so this shows you that you can have topics where much research has been done, but if you look at it with fresh eyes, you can still discover something that people haven't recognized before, which can have a big impact. So then, of course, when this happens, you go back in literature. You think maybe we missed something. And so there is the famous paper by Richards and Wolf from 1959, where they describe the field in the vicinity of a focus in great detail, which you could call a nano-optics paper, because it shows all these very strange, the pointing vector pointing in odd directions and all these things. So they describe all this in much detail. It's a long paper, and in one half sentence they say, by the way, there is a spinning field which spins in a plane containing the propagation direction, which is exactly this transverse angular momentum. But it was just a remark, so they noticed this, and the reason the fact that they wrote this sentence down means that they thought this is something special. But they didn't discuss it further. It was not so obvious what this might lead to. And then the next thing is, in the 70s, there was a paper by Huard and Vigoureux, two French people, written in French, and they wanted to have circular polarized microwaves, but they only had a linearly polarized source, and in microwaves it's not so easy to change the polarization. So they took a big prism, probably paraffine, and sent in the microwaves from the side, so that there was an evanescent wave, and with the proper linear polarization it produces exactly the spinning field with this transverse angular momentum. I mean, not calling it transverse angular momentum. They also didn't talk about the coupling between the spinning direction and the possible emission, if this would be a dipole. But basically they understood these special polarization dynamics there. So I think this often happens, that if there's a breakthrough and suddenly people think, oh my God, this is really nice and has consequences, then if you look in the past, people have been very close to this, but not really doing the final step. And so this, I think, can also be a lesson. If you want to do something new, one should look at the things that people have done, and with all the curiosity and the openness that you have, and then chances are that you discover something new. So I think there's certainly a wide range, and I probably cannot think of all of these, but one thing that I'm struggling with at the moment, and I have a small project on this, is that this sonoluminescence that I started to talk about was a focus of sound wave in a homogeneous medium. And still you had this effect, this small bubble that was created at a scale which is much smaller than the wavelengths of these sound waves. So this we have not achieved in optics yet, and I wonder whether you can do this. When you focus to a small plasmonic particle, gold bead, an atom, you have this enhancement and this near field, which is probably a little bit like it. Then you can have this structure is much smaller than the wavelengths. But then you have to have the structure there. The medium is not homogeneous. And if there would be, due to some nonlinear interaction, so in the case of the sound waves, there surely is some nonlinear interaction. If there could be some nonlinear interaction, then in a homogeneous medium, my feeling is there could be something, but nobody has looked at that. So we are looking, but we haven't found yet. Ultimately, this could even happen in the vacuum, because the vacuum, we know, is not a void space. We know that if you put enough energy, you can create electron-positron pairs, and you can calculate at which electric field this should happen. And so this is far away from what people can do so far. The new ELI project, the Extreme Light Infrastructure project of the European Union, this is one of their goals, so sometime in the future they hope to do this. But maybe it can happen at lower intensities than what they think where it will happen if there is such an enhancement factor. So we have an experiment not in vacuum, because then you need so high, so we don't have the lasers that they have in the ELI project. But you can do this in a homogeneous nonlinear medium, like a gas. So this, I think, from myself, this is a challenge we are tackling at the moment. We are trying to understand and do the experiment. So I think there are some loose ends. Some things, if you think them through, then there are some final things missing, and so to get this, to gain full control of these aspects is a big challenge. And what I mentioned before, all these issues associated with this, what people call the quantum internet, that has many aspects, which is this is full of challenges for the quantum optic side, for the nano-optic side. This transverse angular momentum and directed emission could be a central ingredient to this quantum internet. So this is full of challenges. So we cannot build it now because it has to be, has to have all this flexibility and the steering, but it also needs very low losses. You cannot put up with losses. You need high efficiency, and so that, I think, is a big challenge. So first of all, I know that different people use it completely differently. So I could describe you what different people think of photonics and of optics, which is controversial, or which is not matching. So for me personally, optics is everything. So optics include classical optics and quantum optics, and so this is everything. Photonics is probably a bit weird because it carries the name of the quantum of light, but in the past, during much of my lifetime, it was mostly used by, at least initially, by people in solid-state physics, where the fact that light is quantized does not play a role. They still call it photonics. So that was kind of like a misnomer. But now things are changing. Also, I think if you ask people in Germany and in Anglo-Saxon countries, you get different answers. So in general, things have been changing so much that for me, photonics and optics is two different sides of the same coin. Both basically you can use to describe everything that has to do with light.